Welcome to section 2.2. We're talking about polynomial functions of higher degree. So the last lesson we talked about quadratics, and these are going to be polynomials of a higher degree than just degree of 2. So when we look at these, for it to be a polynomial, for the graph to be a polynomial, it has to be continuous and have smooth curves. So it could look something like this. There's a polynomial function. It also have the smooth curves like it does there. So those are polynomial functions where if it's not continuous, so if you see something like this, where it goes up and maybe there's a solid dot, and down here there's an open dot and goes like that, that's not continuous, so it's not a polynomial. And it also can't have any sharp curves or sharp turns. So if you have like an absolute value graph, the absolute value of x, that's not a polynomial. It has that sharp turn. It has to have a smooth curve. So it has to be continuous and have smooth curves. So we're going to be talking about power functions. Once again, a function, when we look at it in standard form, largest degree, highest variable for the highest exponent of the variable to the lowest exponent to that constant. Now the leading coefficient test talks about what the graph will look like, the end behavior and so forth, based on the degree, the largest exponent, and if the leading coefficient is positive or negative. So when n is odd, when the degree is odd, it's going to, and the leading coefficient is positive, it's going to fall to the left and rise to the right. And that's when a is greater than 0. Now, when the degree is odd and the leading coefficient is positive, so when negative, when a is less than 0, it's going to rise to the left and fall to the right. The way I like to think about it is with a line with a positive slope, or in this case, a line with a negative slope. When n is even and a is greater than 0, it's going to rise left and rise right. It's going to go in the same direction. So think about a parabola with a leading coefficient greater than 1, it's going to open up. When a is less than 0, when it's a negative, think about a parabola opening down. It's going to fall to the left, and it's going to fall to the right. That's what those graphs look like. So if we look at some examples on the next page, using that leading coefficient, coefficient test, we can talk about the end behavior. So our degree n is 4. That is an even degree, and the leading coefficient is a positive 1. So because of that, it's going to have this basic shape to it. So the end behavior, it's going to rise to the left, and it's going to rise to the right. That's the end behavior. For problem number 2, our degree, n, is 5. That's odd. And the leading coefficient is a positive 1. So what it's going to look like is basically like this. Now there might be some more turns that it does, but that's the basic shape. So it's going to fall to the left, and it's going to rise to the right. That's the end behavior. And that's from the degree and the leading coefficient. For number 3, the degree, the largest exponent, n, is 2. That's even. And the leading coefficient is positive. And it's a parabola. It's going to look like this because it's x squared. So it's going to rise left, and it's going to rise to the right. Problem number 4, the degree n is 4, that's even again, and the leading coefficient is a negative this time. It's a -1, so it's going to have this basic shape to it. So what's going to happen is it's going to fall to the left and fall to the right. That's the n behavior, whether it's rising or falling, left or right. And we always go from left to right because that's how we read. We read from left to right. Now, when we're talking about the zeros, remember, for the zeros, when a is a real number, x equals a is a 0. We'll be talking about this. The thing to keep in mind, the zeros are the solutions, are the x-intercepts. So we'll be talking about all those little pieces with the solution and the factors later on. But what I want you to keep in mind is that our solutions are the x-intercepts, are also known as the zeros. Also, that these graphs will have n-1 turning points at most. There could be less, but there's going to be at most n-1. So for this, we can determine the number of turning points. So n is 2, so the turning points is 2 minus 1. So it's going to be, there's going to be 1 turning point there. For number 6, the degree n is 4, so there's going to be 4 minus 1 turning points, which is 3 turning points. And for 7, the degree n is 5, 5 minus 1 turning point, so 4 turning points for number 7. Problem number 8 on the next page. What we're going to do is we're going to find the real zeros and make a quick sketch of the graph using those zeros and using our n behavior. The zeros, the x-intercepts, the solutions. So 0 equals -2x to the 4th plus 2x squared. It's the x-intercept. It's when y equals 0. So what we can do is we can factor this. We can factor out the greatest common factor, which is a -2x squared. And when we do that, we get x squared minus 1. And we can continue factoring this. 0 equals -2x squared, x plus 1, x minus 1. So that's fully factored. Now our zeros, we set each factor equals 0. -2x squared equals 0, x plus 1 equals 0, and x minus 1 equals 0. Divide both sides by -2. X squared equals 0, take the square root, x equals 0. Subtract 1, x equals -1, add 1, x equals 1. So we ended up with 3 zeros for that graph. Now, looking at this, the degree, n, is 4, which is even, and the leading coefficient is negative. So the shape of this is going to have at most 3 turning points. So if we wanted to make a quick sketch of this, I'm going to put it, sorry, that's at -1 and 1, -1, 1, and actually at 0, 0. So there's our 3 intercepts. And what's going to happen? It's going to start down here, it's going to go up, turn, bounce, back up, and then down again. That's what the graph is going to look like. And you can sketch that on your calculators, and you'll see the turning point, one of them, is right on that x-axis. And we'll be talking more about that as we go through this. For number 9, zero equals x to the 5th plus x cubed minus 6x. So what we can do is we can start by factoring out an x. X times the quantity of x to the 4th plus x squared minus 6. What this is a polynomial in quadratic form. So it's x, and we can factor this just like we would factor something with x squared. So the square root of x to the 4th, so it would be x squared here and x squared here, the same degree as that middle term. And now the numbers that multiply to -6 and add to 1 are going to be a +3 and a minus 2. That's as factored as we can get. Now to solve, we said each factor equals 0. X equals 0, x squared plus 3 equals 0, x squared minus 2 equals 0. So we get x squared equals negative 3. And when we take the square root of both sides, we get x equals plus or minus. Now, when we simplify the square root of negative 3, you get I squared of 3. Add 2 to both sides, you get x squared equals 2. Take the square root. X equals plus or minus the square root of 2. Now, the direction said only find the real zeros. Now, that is not real. So we're not going to include that in our real zeros, since that's not a real solution. We're only going to look at our solutions as x equals 0, square root of 2, and then negative square root of 2. Those are our zeros. Now our degree, n, is 5. And our leading coefficient is positive. So it's going to have a shape that looks like this. Now we're going to have at most 4 turning points because it's 5 minus 1. So if we were to graph this, the square root of 2 is between 1 and 2. So it's going to be around here and 1 at 0. So what it's going to do, it's going to go up through that point, down, and up again. This graph actually only has 3 turning points. Remember, the turning points is at most that many zeros, not the exact, turning points. It's n minus 1 is the at most number of turning points, not the exact number of turning points. Okay, now looking at this, we have what are called repeated zeros. So that's when we have a multiplicity greater than 1. So you can see if you have a factor being squared, that would have a multiplicity of greater than 1. So if you look at problem number 8, for example, you see how I had that 2x squared? Because the x squared, we got 0. 0 is a repeated solution. That's why it bounces at that graph. So what happens with this multiplicity? When k is odd, when there's a multiplicity of like 1, so it's like to the first, or cubed, or to the fifth, when it's odd, it's going to intersect, it's going to cross the x-axis at that point. When the multiplicity is even, whether it's squared or to the fourth, it's going to bounce at that point. It's going to intersect, it's going to touch that part on the x-axis, and then it's going to bounce back down. It doesn't cross it, it just turns on that x-axis. So we sketch a graph of these, we apply the leading coefficient test to see what the basic shape would be, find the zeros, and we plot a few additional points, and then we draw a graph. We'll be doing that in the next lesson. Thank you, and I will see you in the next one.